Hi everyone. Today we're going to be going over Lab 2, Motion of a Falling Object. Some key concepts. First is Newton's second law, which says that the net force is a change in momentum over the change in time. And this can also be derived into the velocity update formula. And then the velocity update formula the product of it can be used into the position update formula when the force is changing. That force is changing. And then for force of gravity, the general equation is this g times m1 times m2 over r squared. However, it can be simplified to just mg for specifically near the Earth's surface, where g is equal to 9.8. And then for drag force, there is a drag force due to air particles, and it points in the opposite direction of motion. So for our instance, it's going to be pointing upwards, since the key is going to be dropped downwards, and it can be modeled by this equation. As the velocity increases, the drag force also increases, since it's directly related to velocity. And then as for the free body diagram, this is the key over here starting at the top, and then as time goes on, we can see that the drag force gets bigger since the velocity is going to be getting bigger. But besides that, there's just the gravity force. So for experiment goals and assumptions, we use Tracker to observe and measure the position of the object, and we compared the observed results to two glow script models, one considering drag and one not considering drag, so it just had gravity. And then some assumptions were movement only in the negative y-axis, no other forces acting on the object, rotation, wind, etc. Alright, so moving on to tracker analysis. As you can see, this is the tracker analysis. It's going on this axis. I made sure to rotate the y-axis to account for the weird camera angle, and then I had this ruler behind it, and I dropped this key from here to here. And as you can see in the position versus time graph, in the y-axis, it's pretty quadratic. Looks pretty good. And then this is the data. We'll see it later on. Starting time was 1.7 seconds, ending time was 1.917 seconds. And these are all just like the constants that I used in my code. You can pause the video if you would like to look. And then this is the computational model initial data, so just from the slide before, putting it into code. And then also the equations that I had to code were the Newton's second law and the position update formula. So these are those two lines. And then as for the iteration code, you can kind of see it here. And then when we go through it, we say that the results for the no drag portion is like this. We'll compare all these results later. And then for the model with drag, these are the equations that we had to code. As you can see here, these are the equations, and you'll see them right in here. The initial code was the same as the model without drag, the initial conditions. And then these are the results for the model with drag. Let's move on to comparing them, and as you can see, the tracker analysis definitely aligned best with the model with drag. As you can see, the model without drag ends up a little higher at the end of the time frame than the model with drag. So, and these two are similar. This one's a little bit higher because there's not that force. And then, yeah, so the model that doesn't consider drag force starts to differ from the other two, starting about halfway into the drop. And the model accounting for drag force is very similar to that of the tracker observed data. Some possible errors is human error in tracking the point mass, rounding errors in calculations, and the drag coefficient not being exactly what it has to be. And then lastly, for further questions, as for which computational model determines the terminal velocity, it has to be the one with drag force, since otherwise there would be no terminal velocity. And as you can see for this one, if you look at the velocity versus time, it seems to have an asymptote right around here. And then as for would terminal velocity be the same if there was an initial downward velocity, I put it in and I tested it with a graph, and yes, it would be the same because the initial velocity doesn't affect the terminal velocity. Alright, yeah, thank you so much.